Hey everyone, I'm Carl Wirtz. I'm the Executive Director of Fission Transition, a nonprofit organization working to advance adoption of nuclear power. I'm delighted to be joined today by Roger Holmquist, who began his career in nuclear energy in the U.S. Navy as a submarine nuclear propulsion officer. He worked as a shift supervisor responsible for reactor operations, testing, safety, and maintenance of mechanical and electrical control systems. After completing his active duty, Roger earned his PhD in nuclear engineering at Northwestern University, and in 1979 he joined Argonne National Laboratory, where he specialized in reactor physics, criticality safety, and Monte Carlo methods. Roger put his skills in advanced mathematics to work, improving reactor designs, developing high-performance computing methods for supercomputers, and conducting non-proliferation studies. These are only some of his accomplishments during a career at Argonne that spanned 4 decades. He's here to talk with us today about the future of fast reactors, but before we begin, I want to make it clear that Roger's opinions are his own and do not represent those of Argonne National Laboratory. Roger, thanks so much for joining me today.
You're welcome. I'm glad to be here.
Maybe you could give us some background on the role you played at Argonne developing the Integral Fast Reactor and explain the unique features that set it apart from other designs.
So I wasn't one of the central figures, but I did spend most of my career there working on some of the computing technology that was used for analysis of reactor designs and also, more to the point, for analysis of experiments that were used to qualify the software. So when people design reactors, they use computers. We're not talking about a video game. We're talking about computer programs that have been used and data that's been used to analyze thousands of nuclear experiments. And every time there's a disagreement between the calculated expected result from the experiment and the actual data from the experiment, that gets sorted out and we figure out what the cause is, whether it's an input error, which everyone is familiar with in computer codes, or whether the model embodied in the computer code is insufficient, or whether the underlying nuclear data or other data that's used is incorrect. So there's a huge legacy underlying these computer programs. So when we use them, if there are relevant experiments close to what we anticipate as a reactor design, then we are quite confident that those analyses will be correct and valid. So that was one of my roles in reactor physics, is understanding the neutron chain reaction, which one of my colleagues once said was knowing where the neutrons are and what they are doing.
Okay, so is it a good way to phrase that, that you were doing mostly analysis on data that was collected in the experimentation process?
Yes, a lot of it was what we call critical experiments, which are very low power reactor experiments. There's discussion about what's a reactor and what isn't. These are assemblies of fissionable material that can sustain a neutron chain reaction, and those are used to study the physics of some anticipated reactor design or to tease out some sort of physics issues. And they are called zero power reactors because the power isn't zero actually, but it's so low that you don't need a cooling system. And if you don't need a cooling system, then, well, cooling systems are expensive. And also, then you need a safety analysis to show that the cooling system is adequate in all circumstances. So if you don't even need a cooling system in the first place, these critical assemblies are very useful reactor physics experiment facilities that are quite affordable compared to actually building a reactor and then analyzing the physics of a full-blown, power producing reactor.
And then you can progressively increase the scale to get an idea of how it's going to behave in a real power generation scenario.
Yeah, and you can find errors in the physics. So there's a resonance range in reactor cross sections in which the cross sections vary wildly. We understand that quite well, and we know how to process those. And it turns out that, for example, we had one nagging discrepancy between experiment and calculation that was traced to the use of iron. There's nothing wrong with the iron, obviously, but the way we integrated the nuclear data from iron into the calculation And so we built a special assembly that had a whole lot of iron in it,
Hmm.
and that exaggerated the effect of the error in the iron data, and we were able to untangle that and fix it. And so it was actually a quite serious error. It hadn't affected most reactor designs because most of them don't use much iron. But we chased down all those details. We were very good at going down rabbit holes, some of which turned out to be quite important. And that was the purpose of these critical facilities. And my computer program was written specifically to analyze these critical facilities.
Hmm. It seems like with fast reactors that those kind of potential problems would be magnified just because the flux is so much higher.
You're exactly right. In a thermal reactor, like a water-cooled reactor, the neutrons scatter down to low energy from the high energy that they have when they emerge from fission, down to the low energy where they're going to cause another fission in the chain reaction. And a lot of them skip past this resonance range of wildly varying reaction cross sections. So a fast reactor requires you to analyze properly that resonance range, which is well above the very low energy. So I think it's the velocity of a neutron coming out of fission is slowed down by a factor of 1,000 before it causes a fission in a thermal reactor. And in a fast reactor, it might be not slowed down at all, or maybe just a factor of 5 or 10.
So close to the speed of light, from what I understand.
Um, I haven't done that calculation. I don't think there is nowhere near relativistic physics, if
Oh,
that's what
okay.
you're getting at.
Okay. All right. I think maybe we should take a step back and go over a little bit of the history. If I understand correctly, after World War II, fast neutron reactors were part of our first attempt at using nuclear power for peaceful purposes. Was the funding at the time for nuclear reactors originally driven by the need for bomb material or for generating electricity, or was it kind of a combination of the two?
It was a combination. So at the end of World War II, we had three big national laboratories, Oak Ridge, Argonne, and Los Alamos. And these were assemblies of really top quality physicists, chemists, mathematicians, kind of across the board, because nuclear engineering is a very multidisciplinary field. And so the leaders on the AEC and maybe higher in the political system said, wait a minute, we've got all these fabulous resources, and they're all anxious to go back to their universities and teach and do research. We're throwing away what we could call a critical mass of huge talent and in a technology that we have a strategic interest in, and that was weapons, but also energy. And in fact, Argonne's charter was to explore, the term then was nucleonics, which was the peaceful uses of atomic energy, as it was called at the time. Argonne was founded in 1946. Um, and so it's been doing that ever since. Initially, it was a nuclear energy lab with supporting basic and applied science departments in these other allied fields, like material science and chemistry and so forth. It's sort of over the decades evolved into a science lab with a large nuclear energy program. So that's kind of the history of Argonne in a nutshell. But the focus was always on peaceful uses, and that meant more or less electricity this whole time.
Okay, all right. It seems like from the beginning it was fast reactors, and then during the 1960s, metal fuel that they used was abandoned for uranium oxide. What was the reason for that shift?
We had used uranium oxide in our thermal reactors, our water-cooled reactors. And so I'm not sure the actual reasons, but people were comfortable with oxide fuel, and even people at Argonne were comfortable with oxide fuel, even though we had considered metal fuel. Metal fuel early on had some problems retaining its integrity in the core and so forth. So there were good reasons to like oxide fuel. And once it had been used extensively in water-cooled reactors, then we became quite comfortable with that technology and the behavior of the fuel in the reactor. So any kind of technology, if something works well, you don't just throw it away because there might be something better, although venture into the policy level here, that's exactly what we've done in energy policy over the last few decades. But
Mhm.
anyway, let's get back to the nuclear.
Okay. What was the spark that rekindled interest in fast reactors in the 1980s and finally got things rolling in 1984?
So actually, it was the cancellation of the fast reactor program. Um, that was the Clinch River Breeder reactor, which was a demonstration commercial nuclear power plant, fast neutron, sodium-cooled fast reactor that was to be built at Oak Ridge or near Oak Ridge. And that was canceled by President Carter for non-proliferation reasons. And so since the emphasis was non-proliferation, what emerged from that was a study called the International Nuclear Fuel Cycle Evaluation. And that was a wide-ranging study in which Argonne played a big role. There were other labs in it too. Um, but the idea was to look at all the different potential nuclear fuel cycles from a non-proliferation point of view. What was the plutonium production potential for thorium systems? It was uranium-233. Um, and as part of that, in addition to looking at the weapons material potential of these different fuel cycles, we said, well, we need to look at which of these technologies are feasible, what are their safety characteristics, and so forth. And so Argonne did a lot of that work, and that was when it became noticeable that there were some very nice safety characteristics of metal fuel compared to oxide fuel. And then after that, there were a lot of paper studies for large breeder reactors over the next, I don't know, 5 or 10 years. And I sat in on a bunch of these project meetings with industry people coming in and describing their designs. And some of our folks would talk about our analyses. And it became pretty clear that an oxide-fueled, sodium-cooled fast reactor required a lot more safety engineering of various sorts than a metal-fueled one, equivalent metal-fueled one did. The other thing is the metal fuel has got a higher energy neutron spectrum, and higher energy neutrons means a better breeding ratio, which is a higher production rate of fissile material that can fission than an oxide fuel. The oxygen in oxide absorbs some neutrons and also scatters them down to lower energy much more than metal fuel does, and in fact, liquid metal sodium for that matter.
The oxide is somewhat of a moderator, would you say?
It has a moderating effect that you couldn't call it a moderator. It's not that strong, but
I see.
yes,
Okay.
we call it softening the spectrum.
Okay. um, what really kind of opened my eyes to the fast reactor technology was the book Plentiful Energy, which I'm sure you've read, and I'm sure you worked personally with Charles Till and other developers. In the book, he seems to feel that the IFR's 10-year run was a high point, and that engineers knew they were onto something big. Would you agree with that?
Oh, absolutely. By the way, I do have a copy of that. I've read it maybe a couple of times, and it's actually a very nice description of what working at Argonne was like in the early years, by the way.